Welcome. We will begin today's session with a quick summary of what we have covered in the last class and then build on the topic of discrete time Fourier transform. So let us take a quick look at what are the topics we are going to be covering in today's lecture. We are looking at the contents of Oppenheim and Schaefer chapter 2. Sections 7, 8 and 9. So today we will be looking at the material that is there in section 7 and section 8, which is basically the representation of by Fourier series and some of the properties of the Fourier transform. And if you look at it, we have already looked at what are some of the properties, for example, that the complex exponentials are eigenfunctions of an LTI system. How is DTFT defined? How do we do the inverse formula? So up to that point we have done. So today we'll be looking at some of the properties. But let us take a quick look at what we have covered in the last lecture. We have completed our discussion on sampling and reconstruction. The process of sampling produced for us a signal which is given on the expression on the top left hand side. It has a scale factor. There are many copies of the signal and these copies are shifted by multiples of omega s. They are identical and they are shifted. So in other words, xj of omega is a periodic signal. It is periodic with period omega s. On the other hand, xc of j omega is not a periodic signal, it is a band limited signal, which when we did the process of sampling, we produce these multiple copies. Then we also said that we can recover the original signal by passing it through an ideal low pass filter. So, but for this ideal low pass filter to work, you must take the discrete time signal, create delta functions and then pass it through this ideal reconstruction filter. In case we are not able to do the ideal reconstruction filter because of and also the Dirac delta function, then we said that we could use a zeroth order hold. The zeroth order hold introduces a distortion on the spectrum and that has to be compensated in the reconstruction process. This is what we summarized in our discussion. Then we said that before we do the sampling of a continuous time signal, if we want to ensure that there will not be any distortion due to aliasing, then we have an anti-aliasing filter which is preceding the sampling process. So this will ensure that the signal is, first of all, it is band limited and that it is band limited to a frequency for which Ts is a sufficient rate in terms of Nyquist rate. So let us take a quick example. Let me just ask you to calculate. So this is to reinforce the concept that we have covered in the last class. Supposing I have a sampling frequency of 10 kilohertz. Okay. This means that the sampling period is 1 over 10,000. Okay. Now, what should be the cutoff frequency of the anti-aliasing filter? So, basically I want to know what is the anti-aliasing filter, what is the corresponding omega c cutoff frequency. So, it should be a low pass filter. The anti-aliasing filter is a low pass filter. Remember, our sampling frequency is 10,000 hertz. So, which means that the highest frequency that the signal can contain will be 5,000 hertz. So, the cutoff frequency of the anti-aliasing filter must be 5,000 hertz. So, if you convert that into radians, it will be 2 pi times 5,000, which is the same as 10,000 pi. So, the cutoff frequency of the low pass filter minus omega c to omega c, where omega c is equal to 10,000 pi. Okay. This anti-aliasing filter will guarantee that when you sample at the rate of 10 kilohertz, there will not be any aliasing. So again, keep in mind that the anti-aliasing is an important step to ensure that your sampling process does not introduce any aliasing distortion. And if we take a signal, continuous time signal xc of t, after passing through the anti-aliasing filter, the notation is xa of t. So, xa of t is what we will use for any of our conversion from continuous time to discrete time. Then we said that as you pass through the quantizer, eventually you will represent the samples x of n not with an infinite number of bits, but only with a finite number of bits. We said the total of b plus 1 bit, where 1 bit is used for the sign of the value of x of n, and b represents the fractional period, fractional part, and we will use the 2's complement representation. And again, I won't repeat the material, but I just want to say that the process of quantization is like introducing an error, the green figure that you have. So you take a sample, you introduce a random error, and that produces for you a quantized signal. The minimum and maximum values of the error are delta by 2, and the characteristics of E of n is that it's a random process, and for which we computed the mean and the variance. From that, we calculated the signal to quantization noise ratio and came up with a formula which said the signal to quantization noise ratio is 6.02b minus 1.25, and we did a simple calculation saying, okay, if I have 16 bits of precision, then what is my signal to quantization noise ratio? This is a rough calculation. Now, in this context, I also want you to think of one more aspect. We made an assumption. Okay, so that assumption is important. For this formula to be valid, we made an assumption or a condition. Let me say a condition. Okay, if you remember, the condition that we assumed was that the standard deviation of the input signal was x of m divided by 4. Okay, so now if I change that assumption, that condition, then my signal to quantization noise ratio will change. So just so that you are familiar with calculating the signal to quantization noise ratio, I am going to look at a case, okay, case 1. Now, I am going to ask you to consider sigma x is equal to xm divided by 3. Okay, I will ask you to go through the entire calculation and compute the signal to quantization noise ratio. You will find that in this case, the signal to quantization noise ratio, where all will it change? You look at the overall expression, there will be a log of 2 raised to the power 2b, that will not change. Okay, and then you will have 10 log 10 of 12, that will also not change. The term which contains xm over sigma m, that is going to change, and that is going to have a different value. So you will find that the signal to quantization noise ratio now is still 6.02b, okay, that is still there, and it is now plus 1.26 dB, the total dB. Okay, so you are still increasing. If you add 1 dB of 1 bit of precision, you will still improve the signal to quantization noise ratio by 6 dB. Okay, but the overall expression depends on what you have done in terms of the scaling of the input signal, whether it is xm by 4 or xm by 3, the change. Now, obviously, you can see that xm by 3 is a better option than xm by 4 because the SQNR is better. You're getting a higher SQNR. Why not, make it xm by 2? The reason is, if the input signal is also a random variable, that it can take any value. Now, keeping it at xm by 2 gives you that there is a probability that it will exceed xm at some point because it's a random signal, right? So basically your average value of the signal, if you keep it at xm by 2, then it can actually it can go beyond the signal. So that is where you see that there is a risk that you will run into in terms of the signal going into overflow. To prevent overflow, we take a conservative approach. We say that the standard deviation of the signal, let it be xm by 4. Okay, if you keep it at a lower value, then at a higher value, then you'll get better signal to quantization noise ratio, but you will also have a likelihood that there will be the clipping that will occur at the two extremes. Okay, so with this, we will conclude at least our discussion of the uniform quantizer using the principle of rounding. Okay, rounding is very intuitive. Whenever you want to round a number, if it is, for example, if I want to round 2.7, I will round it to 3. 2.1 rounds it, you round it to 2. So basically, the same principle we have applied. This is very useful when you implement it in a digital signal processing chip, because there you will only have a finite number of bits and all your signals must be represented with a finite number of bits. So therefore, this understanding of this is very important for you to actually be able to implement signal processing algorithms on a processor and then actually do the computation. Okay, so with this we will move on. We introduced the discrete time Fourier transform, the forward transform and the inverse transform, and we proved that the inverse transform was valid, and therefore we treat this as a Fourier transform pair. And Xe of j omega, we can think of it as a real part and imaginary part. We can also take the real part and imaginary part and compute the magnitude and the phase. We call it the magnitude spectrum and the phase spectrum, or the magnitude response and the phase response. Again, this can also be used in our study of the discrete time systems. So we begin today's session with a few examples which will help us to strengthen our understanding of the process of sampling. So let us start with example number 1. Example number 1. So this is an example that we have already looked at. So I just want you to use this as a starting point. The continuous time signal is given by cosine 4000 pi t, and this means that the highest, the sinusoidal frequency f naught is 2 kilohertz or 2000 hertz. We took case 1 where the sampling frequency was 1 by 6000. Okay, the period is sampling period is 1 by 6000, sampling period is 6000. It satisfies Nyquist. So in this case, omega s is 12,000 pi. We will declare this as satisfying Nyquist. Satisfying Nyquist. Okay, now how the spectrum looks like, how to do the reconstruction, we have already seen. But now I want to focus on something different. So what does the discrete time signal look like when you do this sampling process? Okay, so what you do is, this is cosine 4000 pi. Instead of t, we substitute t equal to nts. This is the same as cosine 4000 pi n divided by 6000. Ts is 1 over 6000. So this is what we get, and this gives us the expression cosine 2 pi by 3 n. Okay, it's a discrete time sinusoid which has got a frequency 2 pi by 3. 2 pi by 3 is 360 by 3, 120 in terms of the frequency. It is that's what the radian frequency is. Now remember that the discrete time sinusoids, they will increase from 0 to pi, and then from pi to 2 pi it will decrease, and then the frequencies will repeat. So anyway, right now what we have is a cosine 2 pi by 3 n, and if we want to represent it, we will say that, okay, from minus pi to pi, I have a, not a delta function, but a unit sample function at 2 pi by 3 and minus 2 pi by 3. Okay, so actually I should, if this is 2 pi by 3, then this should be pi, not this. Okay, so this is your omega axis, this is x e of j omega. This is what it will look like, okay, and minus pi also comes closer. Right, okay. So this is my representation of the signal, and we are happy with this representation. Now let's take another case, case 2. This is also something that we had looked at in the class, but gives us another interesting insight. Ts is equal to 1 over 1500. That means your sampling frequency is 1500 hertz, which will not satisfy Nyquist. So, let us put a big X mark and say that Nyquist not satisfied. Nyquist condition not satisfied. Not satisfied. Okay. Nyquist condition not satisfied, agreed. But what does the discrete time signal look like when you do this? So, let us take a look. X of n is cosine 4000 pi n, Ts is 1 over 1500. Okay, if you look at this carefully, simplify, you will get cosine 8 pi n by 3. 8 pi n by 3 can be written as cosine of 2 pi plus 2 pi by 3 times n. Cosine 2 pi n is equal to 1. So, what you are left with is cosine 2 pi by 3 n. Okay, very interesting. Same signal, discrete time, continuous time signal, two sampling frequencies. One of them satisfied Nyquist, the other one did not satisfy Nyquist. However, the discrete time sinusoid comes out to be the same. Okay, let's take one more case. Okay, this is case 3. Case 3. We are changing the continuous time signal. Xc of t is cosine 16,000 pi t. Okay, and we are going to sample it at 1 over 6,000. Okay, what is the highest frequency content? F naught is equal to 8,000 hertz. Okay, 8,000 hertz. So, which means that the Nyquist rate is 16,000 hertz. But instead, what I am doing is I am sampling it at 6,000 hertz. Okay, so clearly Nyquist will be violated. So, we will put a big into mark and say Nyquist not satisfied. Okay, like case B, Nyquist not satisfied. Okay, so what is the continuous time, discrete time signal that we get? So, let us do that. X of n is cosine 16,000 pi n, Ts is 1 over 6,000, 1 over 6,000. This is cosine 8 pi n divided by 3, looks familiar from part B. This is the same as cosine 2 pi by 3 n. Okay. So, observation. Look at case 1, look at case 3. Two different frequencies, okay, produce the same discrete time signal. Same Ts was used for case 1 and case 3. Okay, this was produced. So, basically what we find is more than one continuous time frequency for a given sampling rate can produce the same discrete time signal. So, the question that we want to ask is, are there, so take the case, okay, are there other frequencies? We know that 4000 pi t and 16,000 pi t will produce cosine 2 pi by 3 n if you sample it at Ts equal to 1 over 6,000. Now, are there other frequencies? And so, the question that we are asking is, so write down how many, or are there other, how many continuous time sinusoids sampled at Ts equal to 1 over 6,000. Okay, so basically I am taking these two and from there I am asking this question. Okay, 1 over 6,000 will produce x of n equal to cosine 2 pi by 3 n. Okay, so basically we know that there are two, at least two are there. The question is, are there any others, and how many more can we find that will do for us? Okay, so here is the simple way of visualization and interpretation and understanding that is very important for us. Okay, so let us look at cosine 4000 pi t, sample at t equal to nts, we get cosine 2 pi by 3 n. Okay, this is clear. This is the case 1. This is case 1. No aliasing. Now I want to look at the following: cosine 4000 pi plus m times omega s into t. Okay, so m is an integer. M is an integer. Okay, so m can be 1, 2, and so on, any multiple. Okay. Now, if I want to see what this will produce, t equal to nts, please quickly check. What you will get is cosine of 4000 pi plus m times, what is omega s? It is 12,000 pi. So m times 12,000 pi. Okay, this times n by 6,000. Okay, so basically for ts you are substituting n ts, and if you simplify this, what you will get is cosine of 2 pi by 3 plus m times 2 pi times n. Okay, just calculate it, I mean just simplify this expression. Okay, so this will be cosine 2 pi by 3 n. So any discrete continuous time sinusoid which is shifted by a multiple of the sampling frequency is going to produce for you cosine 2 pi by 3 n. Is that true always? So if m equal to 1, what we get? We get 16,000 pi. Okay, so with m equal to 1, then we get 16,000 pi, which was what we saw in case 3. Okay, with m equal to 2, you can calculate, this will come out to be 28,000 pi. Okay, m equal to 3, it will come out to be 40,000 pi. Okay, so basically, you know, the multiples of the sampling frequency, these are all going to produce for you cosine 2 pi by 3. So if this is the case, then you have an infinite number of sinusoids, number of continuous time sinusoids, which will produce for you cosine 2 pi by 3 n when you sample it at 1 over sampling rate of 6000 hertz. Okay. Now, here is the most important principle that you must keep in mind. Case 1, Nyquist condition satisfied. Okay. So in which case, if you reconstruct, you will get back the continuous time sinusoid. All the others have aliasing. So when you reconstruct, you will get back some other sinusoid. Okay, it will not be the original. So the important thing is, when you satisfy Nyquist criterion, you can recover the original signal. Second point to remember, there could be more than one discrete time signal which corresponds to the sampling in the presence of aliasing. Again, so not to get confused, only when you satisfy Nyquist criterion will you get back the original continuous time signal. Okay. So think about it. This example is important for you to just to visualize what is the process of sampling, what happens when aliasing comes in, why is it that more than one discrete time signal can be mapped to the same continuous time signal, and then under what conditions can we recover the original signal. The original signal can only be recovered when you satisfy the Nyquist criterion. I hope you are comfortable with that, because this is going to be an important aspect of the whole sampling process.